I'm an Associate Professor in Astrophysics at Monash University in Melbourne, Australia. I'm just going to take you through a brief introductory tutorial on programming in Fortran. So if you haven't done any kind of real programming before, the point of a programming language is really to express something in human language or human readable language and get the computer to translate that into its actual instructions, which are very low-level things like push something onto the stack, move to this memory address, pop the number off the stack, etc. So all languages really have the same purpose, and the choice of language is really a choice about what it is you're trying to do. So whether you're trying to write an operating system, and in this case we're going to use Fortran because we're going to try and write scientific software. So we're trying to solve mathematical equations on the computer, and that's basically the purpose of Fortran. So I assume you know something about using the Unix command line. So I'm just going to start on the Unix command line. I'm going to write a simple possible program. And so you can follow along in this tutorial sheet, which is also posted on my website, or it's posted on the Moodle page if you're a student here at Monash. So you could work your way through the document, but I'm going to take you through it live just so it makes sense. So I'm going to use a text editor called Atom. So I'm just going to make a new directory. Let's call it Fortran tutorial and cd into this directory, Fortran tutorial. All right, so I've got a blank directory, and a Fortran program is just a text file. So I could just create a blank text file called hello.f90. So F90 is the extension you use for all modern Fortran code. I'm just going to open that in my favorite editor, which in this case is called Atom. So I'm just going to open this blank document in a text editor. So all we have to do is type the program into the text editor. So we simply type program. I'm going to call my program hello in this case. And a Fortran program always ends in N program, and you can give it the same name. All right, so this is going to be the simplest program in the world. And one of the tricks with programming is not to try and do too much too quickly. So in particular, the philosophy I recommend is really to test what you're doing as soon as possible. So instead of trying to put a whole lot into the program and try to make it run, what you want to do is write a small program and test it, then add a bit more and test it again, and add a bit more and test it again. Because as you'll see in a minute, most of your time spent programming is really spent debugging or finding problems. So this cycle of write a bit of code, test, write a bit of more code, and test it is a very good way of making efficient progress. Okay, so in this case, we're just going to use the print statement. I'm going to print hello world. And that is the end of my program. So what this program should do is simply print out the words hello world onto the screen. Now, Fortran is what you call a compiled language. So that means so I can't simply run this program, it's just a text file. And the thing that converts that into an executable binary is called the compiler. So the compiler that we're going to use is called gfortran. It's part of the GNU compiler collection. So if you're installing it as a package, the package is usually called GCC, so the GNU compiler collection. So if you're searching on the web, for example, you can just download gfortran as a free compiler. So for example, if I type gcc on .gnu.org, then this is the GNU compiler collection. It contains compilers in C, C++, Objective-C, Fortran, Ada, Go, D, and lots of other things. So you can simply download a binary, so the Fortran compiler, for example. And so this is the free open source compiler. It's not necessarily the best compiler, so there's the Intel Fortran compiler, which we often use in kind of real projects, but obviously that's a commercial product that you have to pay for. So for a lot of development, the GNU Fortran compiler is perfectly acceptable. All right, so I'm not going to teach you how to install gfortran on your laptop because I assume that you're going to be operating in your own environment, but usually you can use a package manager. So for example, on my Mac, I would simply do brew install gcc would install gfortran for me. But let's assuming you have this program installed, then you should have a command called gfortran. If you type gfortran, you'll get, and if it's been installed successfully, you should get a message like this if you try to just type gfortran. Okay, so the simplest way of compiling my code is to say gfortran -o. So then I give the name of my executable binary, which I'm going to call myprog. And then you give the name of the text file, which is hello.f90, as the input. So we type that. So what gfortran does is compiles my hello.f90 into essentially an unreadable binary file, which is a series of instructions that the computer then executes. So I can simply run this by typing /myprog, and everything being well, I should get the words hello world on the screen. All right, so that's the very basics of a Fortran program. All right, so that's running the Fortran program. So if you want to know what it's really doing, for example, you can actually see the assembly language that it compiles. So if you type gfortran -s, you get a file called hello.s. And this is what the program actually looks like in kind of computer language. So it's a series of assembly instructions, which is literally, move something in memory to the left, move something in memory to the right. Here is a string, .ascii. So it's a very unreadable document, but this is what the output of the compiler, this is what the compiler does. It takes your text file, which is simply contains, a few lines of human readable text, and it converts it into assembly language, which is then converted into machine code and executed by your chip. But the other point of a language is that this text file is obviously portable. I can say take the same text file to a different operating system or a different machine. But the binary file that you'd produce, so myprog, so in this case, myprog would only run on a Mac. Whereas if you wanted it to run on a Linux machine, you would have to compile it differently. So myprog is not very portable, whereas the source code is a portable representation of what I'm trying to do. All right. So I'm going to start a little bit about why we should program in modern Fortran as opposed to old Fortran. I'm going to show this. I'm going to do this by giving you a very bad example. All right, so I'm just going to clean up after myself a little bit here. But we're going to start with a really bad example. And so I'm going to make a file called in old Fortran style called test.f. All right, so I'm going to open this file in my editor. I'm going to type a perfectly legal program in old Fortran. So old Fortran had many quirks. So if you're wondering, old Fortran was typed in capitals like Fortran shouting, whereas modern Fortran is always an uppercase F and lowercase letters. So modern Fortran is basically anything from 1990 onwards, and this was already 30 years ago. So there's really no excuse for using kind of old Fortran code. Except that, if code has been passed to you and it still works, then Fortran is a backwards compatible language. So that means that old programs will still compile and run. So you can still use legacy code in your project, which is true in many areas of science. You might have things that still work from 30 years ago. All right, but here, so in old Fortran, there were some quirky rules. So for example, you have to type, everything has to be indented by 6 characters, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And this was literally to leave space on the punch card. Now I'm going to give a perfectly legal program. So I equals 1.20. So this program is a classic example of a program that has a bug in it, but being sloppy in the way that you program can actually lead you to waste a lot of time trying to find errors. So the way I'm going to try and teach you to program is to program in such a way that you can pick up your errors very, very easily. So for example, let's do this. So let's compile our test.f. Test.f. So we're going to compile into a program called test. Now I want you to notice that compiled perfectly legally. So there was nothing wrong with the compilation, no errors. And what this should do, of course, is loop over 1 to 20 and print the numbers 1 to 20. All right, so when I run this code, I get the answer 0. So this is a perfectly legal code, but the output I'm getting is not what I expect. So usually in a tutorial, I will offer a chocolate bar to anybody who can tell me why this program is legal. So I can tell you the bug in this program. So the bug is there's a dot here that really should be a comma. So if I replace the dot with a comma, then I get the program functions as it should. So the key problem here was that I made a typographical error, a very small one, but imagine this is part of some much bigger code. So I made a typographical error, and I run my code. There is no warnings. There is nothing that tells me this program is wrong. It just gives a weird output. So the question to you, the viewer, is why is this code legal? And what could I do to help me find this error much faster? So I've already shown you where the error is. What I really made is a typo here when I should have had a comma instead of a dot. But you can see already I'm puzzled by I actually don't understand what this program is doing. And that's because I've programmed in a very sloppy way. So the key message is to use good practices from the start. And this will save you a lot of time. So one of the bad practices in old Fortran, for example, is that there was something called implicit typing of variables. So depending on the letter which a variable started with, so if a variable starts with the letters A to H, it would be a real variable, whereas a letter starting with I to N was an integer variable. So this allows Fortran it allows you to cheat, but what you end up doing is wasting more time in the end trying to find problems which are not flagged for you. So good practice. So I'm going to change this into a Modern Fortran program. So we're going to change the name of the file to F90. And you're going to see straight away why some of these problems would not be there. So let's just rename this file test.f90. Okay, so now, sorry, let's do that again. Test.f90. And then with Fortran 90, we don't need this funny indent by 6. We should write n program bad fort as well. Now I'm going to give the same program, and let's just compile this test.f90, and already I get an immediate error, that there is a syntax error. So that tells me that there's a syntax error on line 3, and it occurs here, right, which is exactly where the problem was with my comma. Now, there's several other bad practices here. So the other bad practice is I should not allow implicit typing of variables. So at the top of every Fortran program, you should have the words implicit none. And now if I compile, then I get 2 errors. And it says the variable I has no implicit type. So that means I need to declare the variable I as an integer as follows. Okay, so now I get back to my previous problem. The second thing is we shouldn't use these labels for the do loops. We should simply use do. And so we don't use line labels anymore in Fortran. We use do I equals 1 to 20. Now you notice that I've left my bug in this program, but it says already there's 2 problems now. It's expecting me to end the program because it doesn't think this is a loop. And there's a syntax error on line 5. So if I fix my syntax error, then it compiles with no problems, and I can run the code, and it does what I expect it to do. So the key is that now it immediately tells me exactly where the program is, and I can fix the problems before I go, launching my spaceship into space. So there's a bit more explanation in the notes about what implicit typing was good for, including the old joke that in old Fortran, God is real unless declared integer. So that's because I still offer a chocolate bar if you can tell me exactly why that old program was going wrong, because why this is legal Fortran is a really interesting question. So I'll still offer that as a reward. Maybe you could leave it in the comments on the video. All right, so the other thing we can do is we could enforce the implicit none flag at compile time. So we could say f implicit none, and that would make sure, even if I forgot to type implicit none at the top here, it would effectively put it in every file for me. All right, so let's move on. So the short lesson there was that what you do in programming often is waste a lot of time trying to find bugs. And so the key is to write your program in such a way that you can so the compiler can very easily tell you where the problems are. All right, so let's move on to a simple mathematical calculation. So I'm going to start a file called maths.f90. So I'm going to open this in my editor, and let's call this program maths, which is what Fortran is good at, in program maths. So every Fortran program, you should start with the line implicit none. So that means you have to explicitly tell it the types of your variables. So I'm going to have a variable which is a real variable called r. I'm going to have a real variable called an area. So what we mean by real is just a floating point number. So these are just variables. So for example, I can set r equals 2, and I can calculate an area, which is pi times r squared. So that's how you do this, the power in Fortran. Now, one thing that really confuses a lot of people is how you should write numbers. So you got to remember that in the computer, there is a difference in the way that you type. So numbers have a type. They can be integer or real or double precision. This just reflects the number of bytes that it's used to store the number in the computer. But it means there's a difference which you don't normally think about. So if I say r equals 2, then 2 with no dot is an integer. So that's of a different type to r, which is a real. So implicitly what's going on in the computer is there is a type conversion where the integer is being converted to a real and that's being set equal to the other real. And you would like to avoid this if possible. So really whatever's on the left-hand side of your equation should have the same type as what's on the right-hand side of your equation. So if I'm setting something like r equals 2, I should set r equals 2.0. Yeah, you don't actually need the 0, you could just do 2 dot, and that would be a real variable. But if you're squaring something, then you should not use the 2.0 when you're squaring something, because what you really mean is r times r. So you should use the integer variable. So the integer 2, because taking something to a fractional power in the computer is a very complicated operation, whereas so it involves a Taylor series, some series expansion of a floating point number to some arbitrary power. Whereas the integer 2 really means just take r and multiply by itself. All right, so that's just the difference. You have to be aware of that when you're writing code, is that the way you write numbers has to be much more precise than the way that you would think about it in everyday life. Now, the other thing we're going to need is the variable pi. So we could simply write pi equals 3, for example, 3.141. But it's better to kind of let the computer do that for you. So a common way to define pi in Fortran is just to 4 times the arctangent of 1. Now this parameter statement simply means that pi is a variable that cannot be changed by the code. So for example, this kind of statement would be disallowed. So I'm not allowed to use pi on the left-hand side of an expression because I've declared it to be a parameter. All right, so and I'm just going to simply print the result here. Print pi is pi, and I'm going to print the area of a circle of radius r is area. All right, so the area is a real variable, the r is a real variable, And again, all we have to do is to compile my program. So gfortran -o, let's call this program maths.f90. All right, now you notice it gives me an error because I tried to reset this pi variable. It says name constant pi in variable definition context. So pi has been declared as a constant, which means I can't have this statement where I try to set pi equal to 3. And that's on line 7 and column 1. So I can delete my line 7. And let's try and compile it again. So I'm just using the up arrow here to go back in my history. You can also type history to go back in your bash history. And you can see all the previous commands you've typed. Another little handy hint is that you can just type G4 with an exclamation mark in front. And that will show you, that will just give you the previous command that started with the match that string. All right, so exclamation mark G4 will just repeat the last command that I typed in my history, starting with gfortran. All right, so my code compiled without problems, and what I should find is I get a value of pi equals 3.141599274. The area of a circle of radius 2 is 12.5663710. All right, so my program seems to be functioning correctly. All right, so we can go into detail about syntax from here, but I think the most helpful thing in this kind of introductory tutorial is really just to teach you how to organize your code. And the key thing when you're programming in any language is to not repeat yourself ever. And you will do this because you've got a nice little routine over here that does a bit of maths, and you just want to plonk it over here to do another bit of maths. And the danger with this is you will always end up fixing a bug in one of these places and you won't fix the bug in the other place. So the key when you're writing code, and this is one of the areas where Python's been very successful, is you want to write code that's reusable. So you would like one function that, for example, calculates the area of a circle. And every time you calculate the area of a circle, you want to use your function. So instead of rewriting, pi r squared everywhere in your code, you want to have a function that does that you use, and this function is debugged. So the key thing is that it takes you a long time to find bugs in code. So what you really, really want to do is to have code that's well tested, that's well debugged, and that only does a quite simple task. All right, so the way to do that in Fortran, so I'm going to drop these other two files, is to put the guts of your program into something called a module. Now a module just means another text file. So I'm going to make a module called geometry. So I'm going to just delete a few things here. Maths, test. So I'm going to delete my programs, and I've just got my text files left. I'm going to delete my test.f90 now as well, and my hello.f90, because I don't need them anymore. All right, so we've got just maths.f90 in my directory. So what I'm going to do is I'm going to shift the actual guts of my program into something like a library. So a library in Fortran is basically a module. And it's not a program that can run by itself. It has to be run, so you still have to have a driving program. But let's put the guts of this program that calculates the area of a circle into a module. So I'm going to open a file called geometry.f90. And now instead of typing program, you just simply type module. So it's module geometry. And now a really good habit, which we're going to get into straight away, is just to write some comments at the top of your module. So a module containing functions to compute the area of a circle. And maybe so give the purpose of the module, and maybe put your name to it, written by Daniel Price, 2020. And so the same thing as a program, you always type implicit none at the top of your module and end module geometry. Now modules are very flexible in Fortran. So they contain a few things. So they contain both variables and functions. So a function So in Fortran, you can have subroutines and functions. So we're just going to put a function here. So a function to calculate the area of a circle. So it's really good practice whenever you're sort of writing Fortran code. And there's different philosophies of code, but I quite like writing code in a sort of functional programming sense. So functional programming means you really you have functions that take inputs. So this is a function. It takes an input variable r, and it's going to output the area given this input r. All right, so I'm going to say real. Now this r should be passed into this routine, which means this routine should not be allowed to modify the value of r. So I'm going to say real intent in r. Now what my function does is just what I did before, pi times radius squared. I'm going to end function area. Okay, so at the top of this module, I can declare my parameter, and this can be shared between all of the functions. So I can have many different functions defined in my module, but these variables up the top are global variables which are seen by all of the functions below. So I'm going to declare pi, 4 times a tan of 1. And the nice thing about modules is you can declare what's visible to the outside world. So for example, I'm going to declare that area and pi are public, but that everything else in my module should be private, so not visible to the outside world. So that means that when you use your module in the other code, the only things you can use is this function called area and this variable called pi. All right, now the purpose of comments is mainly for your future self. When you're writing code, it's easy to remember what you were doing. But later on, it's very hard to remember what exactly was in your head at the time when you were writing code. And so really this is to remind you that when you go back into the code, what the heck was I doing this for? Why did I put this line the way I did it? And so this will save you a lot of pain in the future. All right, so to use this module, all we have to do is change now our program. So we can scrap all of this from our program. We don't need this area anymore. We simply have a real variable called r, and we don't need the definition of pi. And we simply import the things we need from our module. So we use geometry. Now you could just use geometry like that, and that would give you everything which is public in that module. So I'll do that just now. And instead of typing area as a variable, it's now a function that takes in the value of r. All right, so let's now try compiling this. But now I've got two files to compile. So instead of typing minus, so my program is still going to be called maths, but I have to compile both of my my files now, so both maths and geometry. Now you notice I get an error. So it says cannot open module file geometry.mod. So it goes to try and compile my maths.f90 file first, but it can't see this geometry module yet because it gets compiled second. So what I need to do is compile geometry first, and then I can compile maths. So you can see also this is going to save us some pain, and I'll show you some examples in a second. So what we really need to do is we need to compile geometry first and maths second. So maths.f90 second. All right, and then my code will work as it did before. But what it's doing is checking some things. So there's some magic going on here. So for example, say I had an integer variable. So I had an integer irad. And I had irad equals 4. And say I tried to call area with this integer variable. Now in old Fortran, this would just give me garbage. But because I've used the geometry module here, it knows to check that what the area function wants to receive is a real variable. But I've sent it an integer variable. And so Fortran should know that this is incorrect. And when I try to compile my code, it says type mismatch in argument r, passed integer 4 to real 4. So it's checking that what I sent into the function is what this function expects. All right, so what it says is what it should take is a real variable called R. Now the variables do not have to have the same name, so I could call this garbage. Okay, so garbage equals 2, and the error of garbage, and this is garbage, and we could call this 4. Right, we compile this again, we run our code, and everything works. So the name of what a variable is referred to inside the function has nothing to do with the name of the variable that you send into it. As long as it has the same type, then everything's legal. All right. So what this enables us to do is something that in software design and software engineering, this is called unit testing. So we can now test this area module independently of the rest of our program. And that's an extremely valuable thing because it means we can write little small functions which we know are correct and we've debugged. So we know that, for example, so a unit test might simply be send in the value 1 and check, that the error is, so for example, it should be pi minus the area of garbage. So I know that when my radius is 1, that the area should be pi. All right, so if I run this, so a unit test shows me that the error of my function is 0, so I'm getting the correct answer. So it allows me to debug my function, and I can do this one at a time. So that's called unit testing. I've got a small little unit. I can test it independently of the rest of the code, and then I can plug them together to make some, giant program that does something complex. All right, so there's a couple of more things here before we move on. So the first thing is we should allow our compiler to tell us as much information as possible. So the way to do that is to turn on compiler warnings. So warnings are not errors, but they enforce a very good practice. So in Fortran, the flag for this is -w all, which says turn on warnings. So what you should achieve at all times is a code that compiles without any warnings at all. So for example, warnings can be simple things. So if I just declare another variable, I declare garbage and I declare radius, I will get a warning that the variable R is not used. Now this is not an error, it's not a problem having an extra variable here, it's just a waste. And so warnings help you keep your code nice and neat and clean, and it may tell you of something you hadn't intended to do. So for example, say what I was really meaning to use is this variable R, it tells me actually this variable R is not being used by the code. So maybe that's a bug, maybe it isn't, but it helps you to decipher whether your code is doing what you intend your code to be doing. So there's extra levels of warning as well. So you can have -w extra or -pedantic. So these are all useful warnings, and your code should compile without giving you any errors whatsoever. So another little good practice I would recommend is if you're writing modern Fortran code, there is no reason to allow sloppy old Fortran. So if you want to do that, you could enforce a modern Fortran standard. So minus standard equals F 2008 will give you the that your code must conform to the 2008 Fortran standard. And that means that you are not allowed to do some of the old Fortran things which could really mess you up. So if you're compiling legacy code, obviously you would like it to be backwards compatible. But if you're writing code from scratch, it's very good practice to enforce modern Fortran standard. All right, so the last thing we can do is we could use optimization. So we could use minus optimization level 3. So O is for optimization. It's a capital O, not a 0. And optimization level 3 will make my code run fast. Now in this case, the code is not slow anyway. Okay, but you've noticed there's something a bit messy already about having code in multiple files. This is a really, really good way to organize your code, but you can imagine expanding this to a bunch of files. So I've got maths.f90 and geometry.f90, and every time I write some functionality, I want to add an extra module. So I'm going to show you the correct way of organizing this, and that way is called a makefile.